Okay, so continuing with exponential growth and decay models, y equals a times b to the x can be used to model growth and decay. So typically you're going to use the basic form of the standard form of the function when you're dealing with exponential growth and decay problems, like real world problems, where a represents your starting value, which is like your a1 in a geometric sequence. B is your base, known as your growth or decay factor, also known as your rate or your common ratio, basically. And x is the exponent in terms of usually time. Sometimes you'll see them use t instead of x. So the growth rate or decay rate is r, and the growth or decay factor is 1 plus or minus r. So if you have your growth rate, you can't just plug that rate into the function itself. You have to adapt it by either adding or subtracting it from 1. And I'll explain as that comes up in the problem how that works. And then use the factor as the base in all exponential models. So you need to use the factor instead of the rate. That's really important. So let's try example A. It says derive the exponential model for the following situations. So a virus population of 10 doubles every minute. So the easiest thing to do is identify your A value, which is your starting point, which how many viruses do we start with? 10. And then we need to find our growth factor, which is going to be B. So in this case, if the population is doubling, is this exponential growth or exponential decay? Good. So it's growing, it's doubling every minute. So your B value is going to be 2. Because it's doubling. If it were decaying, halving represents decaying factor of 1/2. So how you would set this function up is it would be y equals a times b, and you can either put it to the x or to the t. Either one's fine. We'll use t because it's time, in minutes. In this case, it's in minutes. So whatever you get as your answer is going to come out to be the time in minutes. And that's because they said every minute. So that would be the equation that you have. So do we have any questions about setting up that equation? So in this case, you didn't have to worry about your growth factor, adding or subtracting 1 from it, because it just tells you it's doubling every time. So that one's pretty straightforward. Now for the next question, this is where we're going to have to worry about growth and decay rate and factor. So $1,000 is deposited into an account that earns 3% annual interest. So what's your starting amount of money? $1,000. And you're earning 3% every year, right? Annual is yearly. So this is where you have to worry about the growth factor. So if you're earning 3%, are you gaining more money or losing money? Gaining money. So you're going to take 1 plus your rate. Because if you just multiplied your amount by 0.3, that's going to go down, right? And then 3%, how would I write that as a decimal? Yeah, 0.03. So that's going to be your V value. So see this little formula right here. If it's a growth or decay rate, you have to do 1 plus it if it's a growth, and 1 minus it if it's a decay. So your equation is going to be y equals a times b to the t power because it's time. And this is time in years. So it's important to know when you deal with time, what kind of time we're talking about. Are we talking about minutes, hours, years, seconds? Because when you plug in for t, you need to account for that. If you say you want to find out how much you earn after 37 days, you can't plug in, and you know what I mean? You can't plug in 37 because it's set up for years. So you have to make sure you know what that t represents in the question to plug it in appropriately. So this would be your answer for this question. Next one we're going to look at is C. So the value of a $30,000 car depreciates 20% each year. So what's the car's initial value? Good. $30,000, and it's depreciating, which means that its value is going up or down? Down. So we have to do, when we want to calculate depreciation, your B value is going to be 1 minus your depreciation rate, which how could I represent 20% as a decimal? Good, 0.2, which means your B value is 0.8. So the best way I can explain to you why it's 0.8 is because if your car is losing 20% of its value, what percent of its value is left? 80% of its value. That's why we use that. So it's going to be y equals your A value times your B value to the exponent t time. And in this case, time is represented in what context here? Years. Okay. So if they ever give you an equation and they ask you to find a certain amount, like they say this equation represents depreciation of a car where time is in years, you have to plug in assuming that that time is in years to get the proper answer. So that's a really important factor when you're working with exponential functions that I think can be a little bit confusing. On January 1st, you invest $1,000 in a savings account. The account pays 5% annual interest. How much money will be in the account after 6 years? So in this case, you're starting with how much money? $1,000. And are you gaining money or losing money? Gaining. So it's 1 plus 0.05 is your B. So let's set up our equation. It's going to be y equals A times B to the t power. But this question didn't want us to just set up the equation. This one wants us to do what? Good. Solve for the amount of money after 6 years, which is represented by y. Now in this case, our t is annual, so yearly. So can I just plug in 6 for t? Yeah. Yes, because it's in the right, they're in the same, they're not like one's not in minutes, one's not in hours, they're in the same units basically. So y is equal to 1,000 times 1.05 to the 6th power, which means y is equal to 1.05 to the 6th power times 1,000 is $1,340.10. So that's actually a really good interest rate account. I don't know where you would get one that good. Usually they're pretty bad, but yeah. So any questions about how to do example 4? Alright, so let's try the next one. So it says the world population of the Iberian lynx, that's like a species of some kind of cat, I think, in 2019 and 2020 is reflected in the table. If this trend continues and the population is decreasing exponentially, how many Iberian lynx will there be in 2030? So we know that it's decreasing or increasing. Its rate is exponential, right? So we know that exponential, we're going to have a common ratio, meaning some number, we multiply 150 by some number to get to 120. And that's our common ratio. Does anybody remember how we can calculate a common ratio with the two terms like this?
120 divided by 150.
Good. 120 divided by 150 will help us find what the common ratio is. And in this case, neither of these numbers, well, we can just divide them, and you divide them and you get 0.8. And that would be your common ratio, which is also known as your B value, right? So that's your trend. The population's going down by 0.8 each time. It's actually decreasing by 20% every time, leaving us with only 0.8 of the population left. So now that we know our B value, we can set up our equation, right? So the equation you can set up two different ways. This way makes the most sense to me. The starting population in 2019 to the 0.8 times 0.8 to the... Now, how many years would span from 2011 to 2030? How many years is that?
2011.
Did I say 2011?
Yeah.
I'm sorry. The answer is 11, that's why. So from 2019 to 2030, how many years is that? 11. There we go. That's what I always do. Like, I always say the answer. Yeah. So basically, that's how many years would span from that. So we can calculate the current population using that information, which would be so approximately 12.9. So obviously you can't have 12.9 links. So approximately what, like about 13 of them will be left in 2030, which is kind of depressing, right? They're going extinct pretty fast. So yeah. Do you guys have any questions about how I set up this equation? This is the starting amount, the rate, and the years since. Okay.